Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to perform a quick alignment on the VitaLizer, and I'll also share some alignment tips that you may not know. There's a couple little things that you can look for when you're doing alignment if you don't have any schematic or any alignment data, and I'll reveal those little tips within this video. So let's get started. For those of you that have been here through the entire rebuild and restoration process of this VitaLizer, you realize that this has been an incredibly time-consuming project. For those of you that are just tuning in now for the alignment tips and tricks, if you're interested in seeing the rest of the rebuild series on this VitaLizer, just below this video is the written video's description, and just below that you'll see a show more written in capitals. If you click on that, below that will be part 1, part 2, part 3, and so on of the rebuild process of this VitaLizer. Now, I'm going to be honest with you, I would say only 50%, maybe a little bit more, of the video footage that has been taken on this rebuild process has been published, just because there is so much information and it's so incredibly time consuming. So I just want to share the highlights with you of the rebuild, restoration, and now the alignment procedure. Now there's a whole bunch of alignment procedure gold, I would call it, that I'm going to share with you here. There is no information on how to do an alignment on the wave meter and on the vacuum tube voltmeter of this Supreme Instruments VitaLizer that I can find. So I'm going to share with you some tips and tricks. So if you have a piece of equipment that you have no information on, this will very easily help you identify how to align that piece of equipment, how to align the coils and variable capacitors and things like that. Now, here's the neat thing about this information that I'm going to share with you. This is very helpful even if you have the alignment procedure. This will just speed up the process for you, so it'll make things a little bit smoother. I'm going to be honest with you. A lot of alignment procedures are monotonous and tedious. They take a lot of time, especially in an analog device like this. They take a very, very long time. So I'm not going to take you through the entire alignment procedure, but I'll show you how to align certain key areas, and then off camera, basically I'm just repeating that process over and over and over again, and you don't need to see that because it'll just make this video incredibly long. And again, you just don't need to see that. So I'll show you the very, very key points that will greatly speed up your alignment procedures. And again, if you don't have the alignment procedure at all, this will greatly help with you figuring that kind of stuff out. And that's the kind of stuff that I like to portray on this channel. Now you might be asking yourself, why are you restoring this old device from 1939 to use to repair things? Well, we're going to use this VitaLizer right here to repair modern equipment as well. So we'll be fixing switch mode power supplies and test equipment and all sorts of different things with this device from 1939. You're saying, well, why would you go about doing that? Well, you can pick up old test gear like this for very, very cheap, and you can use older test equipment to fix modern gear very, very easily. What I'm trying to show in the next little bit here, when I'm going to be using this device to repair modern equipment, is the magic is not in the piece of test equipment that you have. The magic is in you. So what I'm going to do now is I'm going to reposition this, and I'm going to start explaining some of the shortcuts and how to figure out how to align the wave meter section of this VitaLizer first. This is the wave meter portion of the VitaLizer right here. Now you might be asking yourself, what is a wave meter? Well, way back in 1939, these were used on the bench somewhat like an early frequency counter or a very selective radio receiver. So here's an example. So say nowadays you want to probe a 10 megahertz standard and you want to see if it's exactly at 10 megahertz. Well, what you do is you just get a frequency counter, and many times the output of a standard is buffered. You just plug the frequency counter into it and it's a direct readout. Things have gotten very simple nowadays. Well, way back in 1939, things weren't so simple. You had to scan the band for the frequency. So say we had a signal at 70 kilohertz. So what we would do is we would make sure the function selector switch is on A, so that's on band A of the wave meter, as you see right there. As you can see up here, it says A, C, E, B, and then D on the bottom portion. So A and C are the upper portion, B and D are the lower portion, and E is just a function that wasn't used with this dial scale in this particular application. So there is no selection for E. So all we have is A, C, B, and D. So right now we're on band A. That means that that's 65 kilohertz, or way back when it would be 65 kilocycles. So say we wanted to find a signal at 70 kilocycles. What we would do is rotate the dial here like so, and when we get to about here or around here, we're going to start to see the needle of the VTVM start to rise. And we'll also see the signal on the scope that's just out of the shot here. As we get closer to 70 kilocycles, as we get right on top of it, we're going to notice a peak. So the needle's going to go to its highest point at that point, and if we go past it, it's going to start to come back down again. So what we're going to do is back this up. We'll notice the needle comes back up again, and if we pass it going the other way, it'll come back down again. So we're looking for the point of maximum amplitude, either on this meter or we can use the scope screen to do that. When we find the point of maximum amplitude, that's the frequency we're at. So just say we're supposed to be at 70 kilohertz, but we don't see anything here. So we keep rotating the dial, and all of a sudden we start to see the needle rise again. We see it rise over here. So we don't have any rising of the needle over here. Nothing's happening down in any of this area. And now the needle's starting to rise up. And as we get close to 750 kilohertz, the needle comes to a peak, and then it starts to fall back down again. So we back this up right to about here, and we find that this is the peak right here. We would know that the frequency that we're looking at is 750 kilohertz, not 700. So you can use this to determine what frequency you're looking at, or what frequency is being fed into this device. Now, way back in 1939, that was a pretty fancy option to have in any piece of equipment. You can locate the frequency of oscillators and all sorts of very interesting things with this wave meter. So very high tech for 1939. So very much like a very selective radio receiver, I guess you could say. And I'll give you an example of this in a bit after everything is all tuned up. So how this works is we have band A right here. So we know right here, this is known as the lower band edge. Okay, so that's 650 kilocycles right there. So that's the lower band edge. And as if we go right to the top here, okay, so we go right up to here, that's 205 kilohertz right there at that last line. So that's the upper band edge. Okay, so that's 205. Now, if we go to band B, that's the second scale down. So if we go back over here, you'll see on the second scale here, we have B. So that tells us that we're here. That's now 205 kilohertz. So from the top of the scale, now we're at the bottom of the scale at the same frequency. So that's 205, and as we go up, we get up to about here, you can see we're at 400 kilohertz now. And as we keep going up to the top, now we're at 650 kilohertz right there. That's on B. So now if we go to C, we go back down to the bottom so we can locate C. So now you can see C is on the upper scale again. Now that's 650 kilohertz. And as we move up, that would be 850 kilohertz. And all the way over here to 2.05 megahertz. Right there, right at the end. So now if we go to band D, over here, again, we go back down to the bottom again. You'll notice that that's the same, 2.05 megahertz right at the bottom band edge right there. And if we go right to the top of that scale, we're now at 6.5 megahertz. That's a pretty high frequency for back in 1939 for a wave meter to be working at. So that's how this works. So what we're going to do is we're going to tune band A, and then everything else, B, C, and D, are just the same procedure over again, just moving the signal generator around and moving the same kind of things around. So I'll show you, give you an example on band A, and then I'll do B, C, and D off camera here. Now the thing is, we need to locate band A on the bottom. We need to locate the coil and the capacitor, and that's what we're going to do here in a few moments. Just before we start an alignment, there's something that we really need to make sure has happened. We need to make sure, first of all, see this little line right here? That line needs to be, when the capacitor inside this unit is fully meshed, it needs to line up with that little line on the window right there. It looks a little bit crooked because of the way the camera is sitting here. So what I'll do is I'll just move this around and I'll give you an example of that capacitor right there. So you can see, pardon the dust and debris and stuff on the chassis here, there's quite a bit of pitting on here as well, as you can see. So you can see that this is fully meshed right down at that bottom portion. Now, if this is not fully meshed, that has to be aligned first, and that's done by loosening off both of those screws, as you can see right there. Both of these screws right here have to be loosened off with this fully meshed at the bottom, and you have to align this dial scale so that that line is in line with the window. And then what you do is you tighten these screws up. Now here's a catch that a lot of people don't realize. Some people don't pay attention to this, and then they do their entire alignment and they realize that, oh, it's not lined up in the window anymore. This here acts as an actual gear reduction itself. When you tighten up one of these screws, it causes this brass collar to move over. So what you have to do is you almost have to overshoot just a little bit so that when you tighten this up, when the brass collar moves from the mechanical motion of that screw tightening on the shaft, it pulls this right into alignment with that meter. So you have to kind of overshoot a little bit and guesstimate. And then once that one is tight, you cinch it up real good. If you tighten this one up, you won't get that movement anymore. Now, this is something that I find a lot of people have done in many receiver restorations, is they think they're aligning the dial windows up right to the, the actual alignment arrow or alignment line. They tighten the thing up and they don't pay attention. They do the entire alignment, but when they bring the capacitor right to the bottom, so when it's fully meshed, that's known as fully meshed. So when all of the plates are together, when they bring it to the bottom, it's out of alignment. So that's fully meshed and that's fully open, okay? So when you see a capacitor like that, that's what they mean by fully meshed. It's just meshed like that. Now, there's a little bit of, as you can see, the gear, it's actually not even a gear reduction, but the reduction unit in here is a little bit soft. You can turn this, but it is pretty tough at this point. So right about here, right about in there is where it's right on its line. And as you can see, pretty much spot on right there, right? So right about there, you can see I'm just touching it. Right on the line. That's what you want to do. You want to make sure that the line on the window is lined up to that line on the actual dial before any alignment is started, and this is extremely important in any type of analog receiver or any type of test equipment. They have different alignment points. Some of them will even have a little arrow on the other side beyond the line, and you align the line in the window to the arrow on the movable dial behind. So it just depends on the particular alignment procedure. Now with this, there is no alignment information on this, so we're just going to use the band edges to align this. Sometimes, depending on the alignment procedure, in some receivers, they won't have you use the actual band edges. So say you were going to align the broadcast band, they would have you align it maybe at 700 kilohertz for the bottom end, and they might have you align it at, say, 1300 for the top end. They won't go down to 550 or say 1700 for the top end. They won't do that. So since there is no alignment information, and this is an extremely accurate device, aligning it at the band edges should be absolutely fine. So we'll just use 65 kilohertz for the bottom end, and we'll use 205 kilohertz for the upper end for the band edges for A here. We won't have to align it at any other place. So say we magically found some alignment procedure for the Supreme Vedolyzer, they may have actually said, okay, align the upper portion at 200 kilohertz and align the bottom portion of the band at maybe 70 kilohertz or something like that. Again, we don't have that kind of information, but I think we can obtain the same kind of accuracy by using the band edges. So I'll turn this thing around. We'll take a look at the coils and the capacitors on the bottom, and I'll fill you in on some of the little tips and secrets to help you with your alignment in a receiver or piece of test equipment or whatever you're working on. On the bottom portion of the Vedolyzer, we have 4 coils and we have 4 capacitors. Here's one of those tips that you want to remember. You might even want to write this down if you think you may forget it. 99% of the time, the coil adjusts the bottom end of the band or the lower frequency, and the capacitor adjusts the upper end of the band or the highest frequency. So things that you want to remember. When you come across a radio receiver like an old Hallicrafters or a Hammerland or Collins or National or any type of radio receiver, whenever you're aligning up the bands in those receivers, each band will have a coil and a capacitor. Again, the coil adjusts the lower end or the lower frequencies, and the capacitor adjusts the higher frequencies. So now what we need to do is we need to figure out which ones are for which band, because we really have no information on this whatsoever. Now, tip number 2 that you want to remember: the more wire that you see on the coil form, so if you find one coil form that has more wire than another one, you know that the one with more wire is the lower frequency. So the least amount of wire that you find on a coil form would be the higher end frequencies. So I'll give you an example of that right now. So what I'll do is I'll just turn this around, and we can kind of see the coils in here already. Okay, I'll just get some light on this here. Hopefully we can see all of them hiding out inside there. We can. That's not too bad. So you can see right here, this coil form has got a lot of wire on it. You can see that it's got 2 bobbins on it. If we look at the one that's over from it, so we can see that one, if I can poke this in here, this one way in the back over here, you see this one in the back? You can kind of see the top portion of the bobbin right on the top there. You'll notice that that one is this coil over here, so that's the second one over. That has, I would say, the second most amount of wire on the coil form, because we can see this other one down here has got less wire on it, and then this one right here has the least amount of wire on it. Well, what does that tell us right away? The one with the most amount of wire is the lowest frequency. So we know right there that this is band A. That's simple. And this can be used in receivers as well. So if you have a receiver with 6 bands, all you do is you look for the coil forms with the most amount of coil to start, so that would be the lowest frequency, and then look at all the rest of the coil forms, and you'll notice that the wire count, or the turns count, will go down and down and down as you get to the highest frequency. So again, you can see that this has got the most amount of wire on it, and this one has the least amount of wire on it. So we know that this one is the upper end. So this one is the highest band, band D, on the face. And this one would be band A. Another way that you can test this, if you're not sure, say maybe a couple of coils look kind of close to each other, just use your ohm meter. They'll usually measure pretty far apart in ohms, and I'll give you an example of that here in just a moment. So there's a real big trick, and that'll help you through your alignment procedure. A lot of the times you don't even need to look at the actual procedure. So when you're aligning most radio receivers, you start with the lowest band first, always, and you work your way up to the highest frequency, because the highest frequency is the most sensitive. So you want to get everything else aligned first, and then you align the last one, because there's a thing known as coupling between some of the coils and some of the receivers. And if you align the upper end first, so say you align the highest band first and work towards the lowest band, when you align all the rest of the bands, it'll actually pull the upper coil off, or the upper band off frequency, just because there's coupling between some of the coils, just depending on the type of receiver, right? So there's another little trick that you want to keep in mind. Always adjust the lower bands first and work your way up to the highest one. So again, we can see it. We have 2 bobbins on this one right here, lots of wire here. On the one just behind it, we've got 1 bobbin, so you can see that 1 bobbin right in the back there. So that would be the second highest amount of wire, and then we would see that one right back in there, third, and then fourth. So that tells us already that this is band A, band B, band C, and band D. Just that quickly, we've already identified what coils do what band. Now, since we can't see behind here, we don't know which one of these coils is going to be tied to these capacitors here. Remember, the coil adjusts the bottom end, and the capacitor adjusts the top end. So what I'm going to do is I'm going to get an ohm meter out, and we'll take a look at each one of these, and we'll see which one is band A, B, C, and D. Looking at the side of all of these capacitors here, all of these variable capacitors, we can see right at the bottom, we have a solder point right here. So there's a lug right there, there's a lug there, one right there, and then one right here. And the wires that are soldered to those lugs all go up to this wafer switch right here. Now, what do we know about more wire and less wire? Well, if we have more wire on a coil form, it's going to have higher resistance because there's more wire there. If we lower the turns count on that coil form, if we take some wire off, the resistance is going to drop. It's going to go lower. So what we want to do is determine which one of these capacitors are attached to which coil behind this little platform right here. Another thing to keep in mind when you're working on any type of radio receiver or any type of a wave meter like this, one end of the coil, almost in all applications, is tied to the chassis, and the other end of the coil, we can call that the top end of the coil, is tied to the variable capacitor. So you can look at it as a coil and a capacitor in parallel. So if you want to draw that on a piece of paper to better help you understand that, that may aid in picturing how this works. So every coil has a capacitor in parallel with it. Again, the capacitor adjusts the higher frequencies and the coil adjusts the lower frequencies. So the coil adjusts the lower end of the band, aligns the lower end of the band, and the variable capacitor aligns the upper end of the band. You'll see that here in just a little bit. So what we want to do right now is determine which capacitor is attached to which coil. So let's probe the bottom one here first. And as you can see, the bottom one, we're just about 1 ohm. So let's go to the second one up, to this one right here. 2.76 ohms. Let's go to the third one. 9.3 ohms. You can see they're in order. And let's go right to the top. 95.57 ohms. So what does that tell us? So this one is attached to the coil with the most amount of wire, right? Because the resistance is the highest right here. So we know now that this capacitor is attached, let's move this out of the way here, to this coil right here. So this coil and this capacitor right here are for band A. This one here has got the second highest resistance reading, so we would know that this coil is attached to this capacitor. The third one, this coil is attached to this capacitor, and this one here has the least amount of coils on it, and we had the lowest resistance right here, so we know that this capacitor is attached to this. So we have the lower end of the band adjustment here for band A, and we have the upper end of the band adjustment right here for band A. Band B, lower, upper. Band C, lower, upper. And band D, lower, upper. Just that simple. So A, B, C, D, A, B, C, and D. Just that simple. These two capacitors here are basically just adjusting coupling through in this amplifier here. And this really isn't a very important thing to be adjusting. These are still glued in place, and adjusting these capacitors is going to make a very, very slight amount of difference just because of, what these are rated at. They're in the picofarads, right? So this thing was so close in its alignment, adjusting these things is really not all that incredibly important. This can just be left alone. And it's the same with this adjustment right back here in the back. I'll just move this so it doesn't fall away. With this one right back here, these are all glued in place still from the factory. Now, what I did with all of these coil forms and all these capacitors is I've loosened them all off already. I've taken these locking retainer nuts here and loosened everything off so that I can get in here and start doing the alignment. A lot of the times before you start doing your alignment, it's a good idea just to check to make sure everything is loosened off, because this is what happens a lot of the time. You'll go through every band and you'll start doing adjustments, and then you say you'll get to maybe the fourth band in. So say you're on band D or something like that, and say it goes to band F. You'll get to band D and you'll find that something is frozen. So now you've got a nut driver, and you're putting force on it with the nut driver, and things are twisting in here because you're using excessive force to try and get something free. A lot of the time, twisting motion, and whenever you're putting a lot of force on something, will sometimes move coil forms around, and it'll cause the rest of your alignment to go out of adjustment. So you have to start all over again. So before you start any alignment in a radio receiver, piece of test equipment, wave meter like this, make sure everything is loose and it moves before you start any of the alignment. If not, you're going to come across one of those situations where you're going to have to redo the entire alignment again. This is very, very important. Another very important tip. Here is another tip for you. You'll notice that these have got a brass shaft with a slot in the bottom here, and a lot of people seem to think that you need to use a plastic tuning screwdriver. Well, here is the exact slug and brass shaft that is in each one of these coil forms right here. I just happen to have a box full of these as replacements, okay? There is enough decoupling from this brass shaft, from the end of this brass shaft, to an actual metal screwdriver. When you're adjusting any coil form like this is intended to be adjusted with a metal screwdriver. You don't need to use a plastic tool. Now, of course, you want to make sure that it's insulated and that you're not touching anything, because there's a lot of live circuitry around. But all of these adjustments are intended to be adjusted with a metal screwdriver. Anytime that you have to insert a tuning tool directly into a slug, so just say there is a slot cut in this slug here, like there are in many receivers, you would need to use a plastic tool for that, because now when you stick a screwdriver into that slug, you're adding inductance, because a lot of the time screwdrivers are magnetized, and you're going to add inductance. But since there is so much brass shaft attached to this, there is a lot of decoupling between this point here and this point here, so you don't have to worry about it, and that's why they made these this way. So another thing to keep in mind. Here's another tip for you, full of tips today. You'll notice that one end of the capacitor is tied directly to the chassis here. Just as I mentioned, a coil and a capacitor are in parallel for each band. If you're ever replacing a capacitor in a radio receiver, so say the nut is stripped out, or say something is wrong with a variable capacitor and you want to replace it, a lot of those square type capacitors you can install either way. Now, only one end of the capacitor is going to be attached to the screw side. The other end of the capacitor is going to go directly to the other side of the capacitor. So if you attach that adjustable capacitor backwards, that means that the screw side is attached to the coil, not the chassis. If you put that capacitor in backwards, what ends up happening as soon as you touch that screwdriver to the adjustment slot or the adjustment screw, it's going to immediately throw everything off frequency. Keep in mind that these are intended to be adjusted with a metal screwdriver. So what I'm going to do here quite shortly, I'll start in with the adjustments here. What I'm going to do is I'm going to grab one of those capacitors and give you an example. They're in a lot of receivers, and I've seen them put in backwards in many Hammerlands. I don't know if it's a factory defect or whether other techs have been in there, but they've put them in backwards, and you just touch the adjustment with the screwdriver and the entire band goes right off frequency. The screw portion always has to be attached to the chassis, so that way when you touch it with the screwdriver, it's basically like you're touching the chassis. If it's attached to the hot side of the coil, again, big problems in adjustment. You'll notice that if you're trying to do an adjustment, you'll touch it and you'll hear the receiver go whoosh, right off frequency, and then you'll take the screwdriver out and you'll hear it go shook, right back onto frequency again. So just another tip to keep in mind, and I'll give you an example of that here in just a little bit. So what I need to do now is I need to adjust this coil and I need to adjust this capacitor right here for alignment on that band A. So I'm going to turn this thing around and I'm going to adjust the coil first for the lower end and the capacitor for the upper end, and we'll check the alignment and see how close this thing actually comes in once it's aligned on band A. And we can expect the exact same results for all the other bands because this thing is just designed so well, right? I'm now ready to perform the alignment on band A of the wave meter. And as you can see, I already have a signal on the screen. I have a 65 kilohertz signal running into the video RF port, and that's been selected right here. So what I want to do is I want to find out where on the scale 65 kilohertz is right now. So we want to see if this is going to read correct. And as you can see, the amplitude is dropping as I go towards 65 kilohertz. You can either use the meter or the scope. As I go over here, you can see I've got lots of signal here and it drops off again. So that there is the point of maximum amplitude. As you can see, the line on the window and 65 are not lining up, so we need to correct that. Now here's another little tip. Whether you're looking at this on the screen or whether you're looking at that on the screen, it really doesn't matter because we're just looking for amplitude. Way back when in the day, a lot of the times this is what techs would look at because the oscillator that they're looking at in the radio receiver or piece of test equipment or whatever is much faster than the oscilloscope. So when you're peaking things up, just looking for amplitude using this is fine as well. As you can see, this goes down and comes up. So either or, whether you have a nice sign on the screen or whether it looks hazy like this, not a problem. And I'm going to show you how to align radios with a screen that looks like this in the very near future. Again, we're going to use some very old oscilloscopes, some very cheap old oscilloscopes that you can find at swap meets for, $5, $10 and use them to align newer equipment. Again, the magic is in you, not in the test equipment. So here we go. You can see as we get to 65, it goes down. So I need to adjust this now so that the maximum amplitude is when the line on the window and the 65 are lined up. So in order to adjust that, I want to bring those two into alignment just like that. And now what I'm going to do is adjust the lower portion of this. So in order to adjust the lower portion of the band, what do I have to adjust? I have to adjust the coil. So I'm going to adjust the coil for band A right now. So here we go. And right about there is where it's at its peak. Right about there. We can actually move just a little bit more. I might be able to get this just a bit closer. Let's try that. That's right spot on. And it starts to drop off on either side, as you can see. Right there is the point of maximum amplitude. So now the bottom portion of the band has been aligned. So now what we need to do is we need to go to the upper portion of the band and align it. Here's the catch. Once we align the upper portion of the band by moving that capacitor around, a lot of the times it moves the bottom off. So we have to go back and readjust the bottom. Sometimes we have to go back and forth a few times until everything aligns up. So let's go up to 205. So there's 205 kilohertz here. Okay, I'll put that right at 205, right there, and I'll adjust my signal generator to 205. So 205 kilohertz, and wow, there's a lot of amplitude there, so I'll turn the amplitude down. And that should correct that. So now let's see. Look at all that. Lots of amplitude there. You also don't want to overdrive the unit as well, because sometimes that will throw the wave meter off. So right about there is a point of maximum amplitude, and as you can see, it's off again at the top end of the scale here. So what I'll do is I'll align this to here, just like so. That looks very close. I'm doing this in the monitor here. And now what I'll do is I'll adjust the capacitor. Again, the capacitor is the upper end, the coil is the lower end. So here we go. And let's see how close that is. Spot on. So now let's see what happened to the bottom end. Let's go back down to the bottom. We'll go back down to 65 kilohertz again. And let's see how close it is. All right, so I got to readjust the signal generator. 65 kilohertz. And here we go. So turn the amplitude up just a bit to where it was before. And it looks like it's spot on, not bad. So let's test the accuracy. Let's move this up to, say, 100 kilohertz, right up to about here, and let's see how close this is. All right, so let's go 100 kilohertz. Looks like we're going to be pretty close. Back this down just a little bit right here. Look at that. Spot on. That is extremely close. And that's the type of accuracy that I would expect out of this machine. And it's the same with all the other bands. I have to do the same thing for B, C, and D now. Exact same procedure, just different frequencies. So that's how you align the wave meter on a device like this. And again, the alignment procedure is very close for radio receivers and other pieces of test equipment as well. Hi everyone, and welcome to Lab 2. So there's a little bit more room in this lab to perform the DC and AC portion of the alignment, and I also have to use a different piece of equipment, actually two different pieces of equipment that are right over here, to perform this alignment, and they just happen to be on a cart in this room. So take a seat right here. Let's perform this alignment together. Before we perform the alignment procedure on the vacuum tube voltmeter portion of the VitaLizer, there's one very important adjustment that we have to make first, and that's the mechanical zero for this meter. So the power switch has to be in the off position, or the power has to be disconnected from the unit to make this adjustment. If a unit has been on for a short period of time, you should let the unit settle for a while before this adjustment is made, just to let capacitors discharge and things like that in the unit. So with the power switch in the off position and the unit being off for, a short period of time, we want to adjust this mechanical adjustment right here until the needle sits directly on the zero line. If it sits above or below the zero line, that will cause inaccuracy in our alignment. So just a very slight movement of this little slot-headed screw here will move this needle around. Now, a lot of people think that they can adjust the 0 volts or the 0 ohms adjustment and basically just try and tune that out. So if it sits a little bit above the line, you can just use the 0 volts to bring it right down to the 0 again. You can't do that because what's happening now is you're fighting the spring tension in the meter. You don't want to do that because, again, it will throw the accuracy of your alignment out. So, power disconnected or power turned off, adjust the mechanical 0 first. After that, the alignment procedure can begin after a brief warm-up time with the VitaLizer. Adjusting the vacuum tube voltmeter in this VitaLizer is a very easy process. There are only 2 adjustments that are variable here. All the rest are fixed resistors, and they were hand-picked at the factory, and they've been taped together, and they don't have any numbers on them whatsoever. Now, thankfully, that's all working okay, and I don't need to replace any of those resistors. So the only 2 adjustments for the vacuum tube voltmeter that we really need to make are the DC adjustment, which is right here, the AC adjustment, which is right here, and this is a trim or a fine adjustment for the AC. So very, very little effect with this particular VR right here. So how I found this out is this says DC right here. Somebody's written this on the chassis. It looks like it could be put there from the factory. AC is written right here, and there is nothing written by this little trim over here. Now I've moved the trim around on all settings in the ohm meter, in DC, in the AC setting, and it does very little. The only place it makes just the slightest amount of difference is in the AC setting. So I found that leaving this very close to the center will yield very good results. So these are the only 2 that we're going to be focusing on today. So let's adjust the DC first. In order to obtain a higher degree of accuracy in the alignment of the vacuum tube voltmeter portion of this VitaLizer, I want the VitaLizer resting on this angle here. This will allow me to get to the adjustments on the bottom here with ease, and having the VitaLizer on this angle will not affect the movement of this analog meter here. Now here's something very, very important to remember whenever you're aligning anything that has an analog meter. In this meter here, on the bottom portion of this needle is a weight. It usually looks like a wound piece of wire on the bottom portion of the needle. If you have the meter sitting on its side when you're doing the alignment will be fighting the weight of this needle, and that will cause a higher degree of inaccuracy in your alignment. So having the meter sitting on a slight angle like this won't hurt, but if you have the meter sitting on a hard angle right on its side like this, you're going to get a pretty high degree of inaccuracy. So something to always keep in mind. The 2 units that I'm going to be using to align the VitaLizer is this Datron 4708 and this Fluke 5440B. Now, the Datron will do everything that this Fluke will do right here. The Fluke really only does DC, but the reason that I have them both on is if I do any high voltage alignments with the Datron, it gives off this really, I guess you could call it an aggravating beeping noise to warn you that the thing is putting out high voltage. This will source 1000 volts, and this unit on the bottom here will source 1100 volts at the jacks here for doing alignments on different types of meters. So the Datron is continually warning whenever you get past a certain voltage level, and it's beeping all the time, and that can get kind of, I guess you could say, aggravating on camera. So that's the reason I have both of these on. So if I do any high voltage DC tests, I'll most likely be using the Fluke 5440B on the bottom. So this will do ohms, it'll do AC and DC and current, it'll do everything. So this is all the options, whereas the bottom unit just will do a DC alignment. That's all the bottom unit will do. So I'll get some leads hooked up here, and I'll let the VitaLizer over here. I'll let the VitaLizer warm up for about 15 minutes or so just before the alignment is started, and we'll get going. The Vedolyzer has been warming up for about 15 minutes now, so the very first thing I want to do is select the range I'm going to do the alignment on. That will be the 20 volts DC range, so I'll select that now. Now what I want to do is electrically zero the meter. You can see the needle isn't sitting on the zero. So what I'm going to do is bring this right down to here, and to my eye, that's pretty much right on the zero. The standard is set to 10 volts output. So that should bring the needle to just about center scale, right on that number 1 right there, if it's aligned correctly. So let's find out. If it isn't, I'll be adjusting one of those resistors on the bottom portion of the chassis. So here we go. And it is just a little bit over the 1. On camera, it looks like it's right on top of the 1 because the actual camera is sitting right about here and it's looking on that angle, but it is just slightly over. So what I'm going to do is adjust that variable resistor on the bottom portion of the chassis. It is somewhat of a touchy adjustment. You can see I'm just moving it a little bit. You can see how quickly that moves. Very quickly. It's very hard to get that right on the center. Right there. That's right on top of the number 1. So now what I need to do is shut the standard off and re-zero the meter again. So I'll shut the standard off. And you'll see that this isn't sitting on the 0 anymore. So I need to re-zero the meter. And now I'll check it again. And it's still just a touch above the 1. So now I'm going to do that again. I'll bring it down just a little bit more. It's right on top of the number 1 right now, so that'd be 10 volts. So I'll shut the standard off again. And I'll re-zero the meter. And try again. And it's getting closer. So what I'm going to do is move this quite a ways down here. I'm going to bring that right below the 1. It seems like as I'm moving it, it's very slowly creeping over to the 1. So now what I'm going to do is shut the standard off. I'm going to re-zero up the meter this way. Right there. And I'll turn the standard back on again. And now it's right on top of the 1. So that's right on top. So you can see, going back and forth between the 0 and the adjustment, I saw that it was moving up very, very slowly, or moving down, I should say, very, very slowly. So I brought it down quite a ways, and I tried it again, and that brought it right on. So there's somewhat of a ratio going on between the 0 volts and that adjustment on the bottom. So now let's try it at 15 volts. So what I'll do is I will move this. I'll shut this off here. And we'll try 15 volts. Enter and on. That's spot on 15 volts. So let's try 5 volts. 5 volts. Enter. Spot on 5 volts. So that is extremely accurate. And that is the end of the DC alignment for the VTVM. Just that easy. So next, we'll do the AC adjustment. Let's align the AC portion of the vacuum tube voltmeter in the Vedolyzer. So what I'll do is I'll put this onto the AC voltmeter setting. I need to re-electrically zero the meter now. So I'll do that right now. And the same button is still pressed. So this button is valid for the 20 volts DC scale and the 30 volts AC scale. The 30 volts AC scale is right on the bottom here. So that's 30 volts, 20 volts, and 10 volts right there. I have the standard set to 20 volts. Let's see how accurate this is right now. So here we go. And it could definitely use an adjustment. It's a little bit low. So what I'm going to do is Adjust this here. Right to about there. I'll turn off the standard and I'll re-zero everything. Very, very close. I'll turn that back on. And just a little bit below the 2, so I'll adjust that again. And what I'll do is shut this off and re-zero this. Try again, turn it on. And that's pretty much right on top of the 2 right now. So let's try 30 volts. 30 volts will be right at the end of the scale here. Look at that. Spot on. Let's check out the accuracy of the ohm meter in the VitaLizer. So in order to use the ohm meter, we need to put the function selector switch onto ohms. It's on ohms right now. See, that's ohms right there. Now, in order to align the ohm meter, it's a little different than normal. So with no test leads, you have to adjust the 0 ohms so that the needle is at this end of the scale. So you can see it moves this around. So right about there is at the end. Now we need to short the test leads together and adjust the 0 volts for the bottom end of the scale. So we adjust this. You can see that we move this end around. Right about there is looking at it straight on, right about there. It's very, very close. So if I open the leads again, it should go right back up to the top and rest where we set it the first time. So I'll plug the test leads into the standard. Now I've left the button on the same setting, so that means that we're on the top scale here. So that's 1K, that's 10K, that's 100K, and that's 1 meg right at the end. So let's test out its accuracy with 1K ohm. So I'll turn on the standard here. And as you can see, it's right on 1K ohm. So let's test it at 10K ohms. That's that line right there. Not exactly right on top of the 1, but very, very close. That is totally acceptable. Let's try 100K. So that is 100K right there, and it's very, very close. And 1 meg should be right at that little line right there. You can see it kind of has a bit of a turn in the line right at the end. Let's try that. And as you can see, no problems right on. And what I'll do is I'll shut this off, and it should go forward just a little bit. There we go. So all in all, this thing is working incredibly well, and that is all the original resistors in this thing being used for the ohm scale in here. None of those resistors have been changed. That is absolutely amazing that this thing is so incredibly accurate. Dealing with a needle's width in the ohm scale in a meter like this is absolutely nothing. Very, very impressive for its age. So all in all, the VitaLizer is working, and it's a definite success. So what I'll do is I'll just back this out here. So now the VitaLizer is going to sit right there on the old-time workbench, and we're going to use the VitaLizer very shortly to service modern gear and antique gear alike. This should be a lot of fun to use this device. Earlier on in the video, I mentioned an adjustable capacitor where one side is attached to the screw, and these are very common now. So this side here is attached directly to the screw, so there is continuity between the screw, the adjustment screw, and this side right here. So if this was to be installed in circuit, this side would have to go to the chassis, and this side here would go to the coil. If you installed this backwards, even if you used an insulated screwdriver with a small metal tip on it, as soon as you touch this, it would detune the circuit in many cases. So something to be aware of. Now, many of these trimmer capacitors are also insulated as well. So the screw in the center is insulated from both sides. It just really depends on the application. This one here, again, there's low ohms or continuity between the screw in the center and this side. Very, very important to know this capacitor's orientation in circuit. In the previous video, in the trivia question, I asked, what is this? So if you're just tuning in now and you want to guess what it is, I suggest you pause the video, think about it, take your guess, and I'm about to tell you what it is. This is basically a filter. It's a noise filter. So this would bolt to a chassis. There's a capacitor in here, and this would act as a feed through, and it's just to cut down noise in any type of an atmosphere where you have a heavy current. You can see that this will deal with up to 20 amps passing through this device, and it'll filter noise off that line, so commonly used in the power lines of radio gear and things like that. So this is basically just an inline filter that would bolt to a chassis. That's all that is. And now, for the next week's trivia, what is this thing? I'll give you a bit of a hint. That's all you get. What is this device right here? Thanks for stopping by the lab today. I hope you're enjoying these videos. If you are enjoying these videos, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid state electronics alike. So there'll be a lot of repairs, restorations, troubleshooting procedures, and even some circuitry design on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you want to be notified as soon as I upload a video, don't forget to tap the bell symbol. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you're going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description, and I'll also pin the link at the top of the comments section. So if you click on the link, it'll just take you right there. All right, until next time, take care. Bye for now.